In this series of lectures, we're going to talk about a method of solving integer programs called column generation. The main idea behind column generation is that we exploit some decomposable structure inside of our integer program. So before we talk about column generation, we're going to talk about decomposable problems. Throughout this series of lectures, we're going to continuously introduce new notation for decomposable problems. The notation will fit the setting. The first decomposable problem we're going to talk about is sort of this one in front of us. In this case, we have some objective function. It's maximizing the sum over all of I of c of I, a constant, times the variable x of I. Inside of this objective function, though, we've decomposed all of the x variables. We've decomposed them into sets, s1 through sk. For each one of these sets, there's a particular constraint. In this case, we've said that the sum of all the i's in S of I multiplied by dij is less than fij. There's one of these constraints for every set Si. Note that in each one of these constraints, the only variables that appear in only one of the sets. For example, in this first constraint, only the variables in S1 appear, whereas in the bottom constraint, only the variables in Sk appear. These constraints are the decomposable constraints. Just so we're clear here, the quantities dij actually form a matrix. Each one of these constraints can be thought of as some sort of matrix type constraint. In addition to these decomposable constraints, there's also another constraint, the link constraint. The link constraint involves all of the x variables. The link constraint is what prevents us from solving a set of separate integer programs instead of, say, having to solve one integer program. For right now, we should just focus on notation. We're immediately going to see another version of this notation. We're going to vectorize it, and the vectorization might make things more clear. For now, all we should focus on is the fact that the variables themselves, the xi's, are separated into different sets, S1 through Sk. There's a constraint for each one of these sets, and there's a link constraint that links all of the sets together. Here's our second form of notation. Immediately note that we've gotten rid of a lot of the summations. The summations in the previous notation were really just hiding the fact that we're multiplying matrices and vectors. So, for example, when we look at the objective function, instead of having summations, we have dot products. In this case, we have the dot product of a vector of constants, c, multiplied by our variable x. There's a little bit of strange notation here in that we have a superscript on our x variable. This x variable is actually an x vector. The size of this vector is the size of the set S1. There's a number of variables equal to the size of set S1. The same is true for all the other vectors. x2 has the size of set S2, and xk has the size of sk. Our objective function now can be written as a sum of dot products. We can also write the decomposable constraints. In this case, the sum of all the dij's times the xi's can be written as the matrix d1 times the vector x1. This is the same vector x1 where the number of entries is equal to the size of the set S1. Here we multiplied by a matrix D defined by the constants in the previous notation. This is all less than some vector f1. We do the same for all the constraints, all the decomposable constraints. We write the matrix D, d1 through dk, and multiply by the vector, or the corresponding vector, x1 through xk. We set these less than or equal to a vector of constants, f1 through fk. Additionally, we have the link constraint. And now we can see why this link constraint links things together. We have a matrix A1 multiplied by the vector x1. But now, instead of having a different constraint for every matrix A, we sum up this constraint for all the entries x1 through xk, and set it less than or equal to b. In this way, the link constraint links all these vectors, x1 through xk, together, whereas the decomposable constraints are individually defined, one for each of the xk's. One feature of this new notation is that we have to write our variable xi as a 0, 1 vector with the size of set Si. In this case, we're going to use Ni to denote the size of Si. So xi is in 0, 1 to the Ni, meaning that there's Ni entries, all of which are either 0 or 1. Before we get into column generation, we're going to take a look at this particular notational version of a decomposable problem and see exactly why we call this a decomposable problem. Our main tool for doing that is going to be introducing a Lagrangean relaxation. If you don't recall Lagrangean relaxation, we introduced this very early on in the course when we were talking about obtaining upper bounds. In this case, we're going to use the Lagrangean relaxation again, and although we are explicitly going to find an upper bound using Lagrangean relaxation, the more important point is that by taking Lagrangean relaxation, we're going to show how this problem can decompose easily. To do that, we look at our particular notational variant of a decomposable problem. We're going to take a Lagrange multiplier, in this case lambda. Lambda in this case isn't just a particular number, but actually a vector. This lambda vector is going to multiply the top constraint, our so-called link constraint. And keep in mind that this link constraint is actually defined as a vector. It's a vector times it's a sum of vectors times matrices that are less than or equal to a vector. When we do this, multiply by our lambda Lagrange multiplier, we do the procedure for the Lagrangean relaxation. To do this, we rewrite our objective function, where we have our old objective function, c1x1, but also multiplied by the vector lambda times the amount that a particular constraint is violated. In this case, we've taken our vector lambda and we've decomposed how it interacts with each of the terms. It's easy to see that by decomposing this lambda into its influence on x1 through xk, we actually recover the Lagrangean relaxation for this constraint in general. By writing it in this way, though, we can see that it's decomposable. Just to make sure that we're clear, our objective function includes the constant term c1 times x1, but also a term associated with how much the constraint is violated, multiplied by the term lambda, our Lagrange multiplier. The constraints in the linear program now only consist of the di's times the xi's less than or equal to the fi's. For now, don't be confused about this vector notation. Although we haven't seen a lot of dot products in our objective function, this is really just saying that we're summing up a lot of different terms. We're summing up ci times xi, and then lambda I times bi minus a vector a times xi. We could expand out our vector notation to get a lot of summations, but it's a lot uglier, and it won't get us at the core idea of decomposition. Now that we have the Lagrange multiplier and moved one of our constraints, the link constraint, up to the objective function, we can now solve k independent subproblems. In this case, our subproblem is defined for each one of the i's. Our subproblem looks at a particular portion of the objective function associated with xi, looks at the constraints associated with xi, which is dixi less than or equal to fi, and searches over a set of vectors xi in 0, 1 to the ni. This is a vector that has the size of si. Because the constraints for all the xi's are now completely decomposed, that is, if we have a vector x1, it only appears in these constraints and no others, we can solve k independent subproblems. After we solve these k independent subproblems, we can get the objective function by adding the objective values of all these k different subproblems. This is the key behind decomposition. We have some original problem. Our original problem has an objective function that involves all of the xi variables, and then there's some special set of constraints. Each set of these constraints involves only some set of the x variables. We also have some link constraint. The link constraint involves all of the x variables. If we were able to remove the link constraint, for example, by taking a Lagrangean relaxation, then we could decompose our problem into k distinct subproblems, one distinct subproblem for each set of x variables. Then we can reconstruct the objective function by summing up the objective functions of each of our k subproblems. The Lagrangean relaxation is one method to exploit the decomposition. We're not actually going to continue with Lagrangean relaxation. Instead, we're going to use a new technique that's going to result in a new way to solve integer programs. As a prelude to this new idea of column generation, we're going to improve on our notation once again, or rather make it more readable. We're going to turn our vectorized notation into what we're going to call the compact notation. This really isn't too big of a change. Effectively, for the objective function, instead of writing this as a sum of dot products, we're going to write this as a summation. We're going to do a similar thing for the link constraint, writing it as a sum of matrix times vectors less than or equal to the vector b. The main notational difference is that we're going to write our link constraint. For example, this d1 x1 is less than or equal to f1 constraint in a little bit of a different way. We're going to introduce capital Xi. Capital Xi is going to be the set of feasible vectors that satisfy this particular link constraint. In this case, Xi is going to be the set of vectors, remember x superscript I is a vector, in 0, 1 to the n, so that this vector satisfies our decomposed constraint. Now, instead of writing the constraint that d1 x1 is less than or equal to fi, we're going to write the constraint that xi is in the set of points capital Xi. In effect, these two things are equivalent. The link between them is the definition of xi. It's useful to just think briefly about exactly what this notation is saying. Effectively, instead of saying that we're going to look at linear constraints, it's telling us that we're going to look at one set of linear constraints, the link constraint, and for all of the other constraints, we're going to compact them into just feasible sets. In this case, the feasible sets are xi. Now that we have this notation behind us, we'll see it in the future. Now we'll have an idea of what column generation is going to be. The idea behind this new technique of column generation is that we're going to first enumerate all of the feasible points. And now we can see why we made this notational change. Instead of talking about sets of linear constraints, we're talking about sets of feasible points. If we're going to enumerate a set of feasible points, it's easier to think about this as a set capital Xi instead of as a set of linear constraints d1 x1 less than or equal to f1. After we enumerate all of the feasible points, we're going to reformulate this integer program. This integer program is going to have a huge number of variables. Each one of the variables is going to correspond to exactly one of the feasible points. You can see why this could potentially be huge. The number of feasible points for a particular program can potentially be enormous. After we reformulate this IP, we really can't solve it because of the huge number of variables. So we're going to introduce our solution technique called column generation. This solution technique of column generation is going to iteratively add columns. Columns here are going to be variables. By iteratively adding columns, or variables, we don't actually have to deal with the huge number of variables. Instead, by using this iterative process, we can potentially solve smaller integer programs to get a solution to our original one. We'll see the idea behind this technique. The first thing we're going to explore is enumeration of all the feasible points and the reformulation of the integer program. After we look at the reformulation of the integer program, we're going to look at the specific technique that iteratively adds columns.